Okay.
Okay.
So yeah, so you can start.
Yeah. So today I'll talk about Riemannian connections. The idea is to find a preferred connection that's called the Levi-Civita connection, and that is in a certain way compatible with the metric, and well, has another property that makes things easier. Okay, so now yeah, so the idea until now we had been working with an arbitrary differentiable manifold. I mean, connections are defined in arbitrary differentiable manifolds, and we now want to ask the following question: what happens if instead an arbitrary differentiable manifold, we fix a Riemannian manifold, right? So is there a way of finding a preferred affine connection? And this leads to the concept of Riemannian connection. Okay, so the definition I chose for Riemannian connection is the following: having fixed a Riemannian manifold, an affine connection is compatible with, yeah, it's compatible with the metric given to the Riemannian manifold if for any smooth curve gamma and any pair of parallel vector fields P and P prime along gamma, we have that the metric evaluated at the pair of vector fields is constant. Okay.
Yeah. So one question. So you mean that each of them is parallel along gamma, right?
Yeah.
Not that they are somehow parallel among each other, right?
No. That they are parallel along gamma. Yeah, each of them, not between them. Okay. Now, there are two equivalent ways of saying this. One of them is the following. That is more or less the reason for which one wants a connection that is compatible with the metric. So if we have a Riemannian manifold, a connection on M is compatible with the metric if and only if for any vector fields V and W along a differentiable curve gamma, we have that we can differentiate the metric evaluated at these vector fields as a function of time by the usual rule of differentiation, right? So yeah, that's essentially what being compatible with the metric means or allows us to do. The reason for which I did not choose this as the definition of being compatible with the metric was because originally I thought that with this definition, it was easier to prove another equivalence, but I think I thought that I made a mistake there, but I'll get to that in a moment. Okay, so to prove this, to prove this, if this equation holds, then clearly the connection is compatible with the metric, right? Because the derivative of this function will always be 0, since in the case in which we have two parallel vector fields, right? Because by definition, the covariant derivative of a parallel vector field is 0, so the first term is 0, and in the same way the second term is 0. Okay. Now, for the converse, we can choose an orthonormal basis for, I mean, we fix a point. We choose an orthonormal basis for that at that point. Yeah. And we can extend the vectors that give that orthonormal basis by parallel translation along gamma, right? Each of them we extend separately. And since the connection is compatible with the metric, at any given point in time, the corresponding frame is still orthonormal, right? Because compatibility with the metric guarantees that angles are preserved. Okay. Yeah. So we have built not exactly a local orthonormal frame, but at least a frame along the curve, an orthonormal frame along the curve gamma. And in terms of that frame, we can write our two vector fields like this. I think I missed, yeah, here I'm missing V equals the sum and W equals the sum. Now, since the vector fields PI are parallel, then the covariant derivative of V and of W in terms of this expression will look like this, because when we apply the rules of the covariant derivative, we first use linearity and then we use the Leibniz rule, right? And the second term will be eliminated because the vector field is parallel, right? So we have this and we have this, and then we simply evaluate this sum here in terms of these two expressions. We get this because the frame is orthonormal, and yeah, that this is precisely the expression for the differential of the sum that in the orthonormal frame is exactly the metric evaluated at P, W. I mean the differential, yeah, that. And that is what we wanted to show. So now, this is the second equivalence of a metric being compatible, of a connection being compatible with a metric. So the idea here is very similar, right? That if we have three vector fields defined in a whole manifold, and we let one of them act in the function given by evaluating the metric in the other two, then the vector field acts similarly to this rule, right? The action is given by evaluating the metric at differentiating the first one in the direction of the vector that is acting in the function, and the second term is given by evaluating the metric in the first vector, along with we're differentiating the second vector in the direction of the vector that is acting in the function. So one direction of this is simple to prove, and the other one is not simple at all. Okay, so suppose yeah, we have a connection that is compatible with a metric, and we have a point in a fixed point in the manifold, and we then fix a curve, a smooth curve, such that at time t0, it has value the point P that we fixed before, and such that its differential at the time t0 is exactly the value of the vector field x at the point P. Okay, and then we know that we can calculate the action of the vector field at the point P in the function given by evaluating y and z in the metric by differentiating this, okay, where we restrict the vector fields y and zeta to the curve. I mean, this is like, yeah, we restrict the whole function g to the curve, but that is the same as restricting the vector fields to the curve. And then differentiating with respect to time. And then here we are using that the connection is compatible with the metric, then we can use the previous proposition to differentiate. We have this. Now we use that both y restricted to gamma and zeta restricted to gamma are extendable. So as to express the covariant derivative in terms of the connection. And and here I'm actually skipping something, right? Because there we would have in terms of the connection evaluated at gamma prime of t0, but gamma prime of t0 is precisely x evaluated at P, right? So this allows us simply to put, instead of gamma prime of t0 here, x evaluated at P. It's exactly the same in the other parts. So we arrive to this. And that's exactly what we wanted to prove. Now, this proposition is the reason for which I chose the definition that I chose of connection being compatible with the metric, because I thought the converse was easier this way, but actually not, because I mean, we would like to say, okay, now if we want to go from here to concluding that the connection is compatible with the metric, we need to fix two parallel. We either need to. I mean, a way of doing it would be to take two parallel vector fields and showing that if we evaluate them, two parallel vector fields along curves, a curve obviously, and showing that when we evaluate them at the metric or in the metric, the value is constant for every time, right? But the problem is that when we want to do that, we will most likely want to use that this holds, that we can differentiate with respect to time like this. And the problem is that when we try to do that, we will implicitly be assuming, we try to pass from this inequality to that other inequality, to that, from this equality to that equality. But when we do that, we are assuming that the vector fields that we are working with are extendable. And that isn't necessarily true. So that's what complicates the proof. A way I saw in a book that they solved this is by working in local coordinates, but the proof is really, really, really long. I read that Milnor uses another strategy where he defines things a little bit different, but I don't know if then how easy it is to show the equivalences between the definitions. This definition I took it from Carmo's book, but I do think at the end of this proposition, Carmo says the converse is trivial. And yeah, and I'm quite sure that that's a mistake after thinking about it for a while. But yeah, the proof is not conceptually difficult, but it's really, really long because you have to do a lot of calculations. You work in local coordinates, you evaluate things, and just go on and on and on using obvious identities. But yeah, I don't think it is that interesting. Now, anyway. So, yeah, if we only think about connections on Riemannian manifolds that are compatible with the metric, we can construct many of them. Actually, the same strategy for constructing arbitrary connections in a differentiable manifold works for constructing compatible connections compatible with metrics. I mean, we construct them locally and then we paste them with partition of unity. So we have to look at something else, right?
Just one question.
Yeah.
So you are saying that the vector fields may not be extendable, right? But
yeah.
Like even if you assume them to be like of class C infinity to begin with on the curve, they may be not extendable.
Yeah, I was reading about that. I'm not exactly sure. I mean, I do not know an example, but I know that there are examples, and I think that
or could it be that it may be that it is because the curve may intersect itself or something like that. So if it crosses itself, then and you have a vector field on the curve, then you really have like two vectors attached, right? Like one for there are 2 points on the interval at which you hit the same point on space, and then at that point on space you have a one tangent vector for each point on the interval. Could it be that instead?
Yeah, that might be one possible reason for which a vector field would not be a smooth vector field along a curve may not be extendable to a vector field defined in the whole manifold, right?
Right, and then I can imagine that then working on local coordinates somehow allows you to kind of to deal with both, with both instances of the crossing of the self-crossing separately, I guess.
No, more than that, it's. I mean, you simply do not have to extend vector fields.
So, sorry, can you say that?
That then it isn't necessary to assume that the vector fields defined along the curve are extendable, or yeah.
Okay, all right, okay. Well, okay, anyway. Okay,
now, yeah, so the thing is, we still have no preferred connection. So yeah, we should look at some other characteristic property of the usual connection, or of the usual way of differentiating vector fields, along vector fields in Rn, right? So yeah, that's something I did not mention, but obviously a connection in Rn is given by differentiating one vector field in the direction of another vector field. And that's actually, I mean, we will see that kind of connection is the connection that interests us. But so yeah, we can think about an arbitrary connection, and we take the difference between differentiating two vector fields, one in the direction of the other, in local coordinates, of course, at the moment. So by the calculations we did yesterday, in local coordinates, this first term will be the sum over k of this plus this other sum indexed by ij, right? This first sum. And then the second term will be this plus this other sum right here, where the Christoffel symbols appear. Now, we can notice that if we leave, if we just look at these differences, then this is precisely evaluating the Lie bracket of the vector fields x and y. And actually, in Rn, since the Christoffel symbols will be 0, these other terms do not appear. So, and one could ask or could think that the only way for these terms, for this extra term not to appear, is if the Christoffel symbols are 0, right? But there is another possibility, and that is if the Christoffel symbols are symmetric. I mean, symmetric in the sense that they fulfill or satisfy this equation, right? When we change I and j, we obtain exactly the same value. If this is true, then this cancels out, right? Because
but wait, that's kind of not completely clear to me, because in that sum, you see it's xi yi, and then it's minus yi xj.
Yeah. So
even if gamma ij is equal to gamma ji, so what do you do?
Yeah, you should separate this into terms. Then you change the symbols in one of them. I mean, you change them by symmetry. And in the other case, you can change the indexes, right? The dummy indexes, and then they will be eliminated with each other. In one term, you use symmetry, and in the other term, or in one sum, you use symmetry, and in the other sum, you change the dummy indexes. I mean, you change I by j.
Right. So let's say you have the pair ij in the index, the pair of indices I, or the ordered pair of indices I comma j, and then you are saying, okay, let's say the first term, leave it there, and then the second term, which is yi xj gamma ji in that case, that switch it to exchange it with the term that appears with the ordered pair j comma I. That's what you're saying. Is that what you're saying?
Yeah, I think that's what I said.
Yeah. Okay. Yeah. Okay.
Okay. Yeah. So yeah, if the
I agree. Yeah. Then I agree.
Yeah, if the Christoffel symbols of the connection are symmetric in this sense, then this difference should equal the Lie bracket, should be equal to the Lie bracket. And when that happens, we will say that the connection is symmetric or torsion-free. Actually, this difference, people normally call it torsion, right? And if the torsion is 0, we call the connection symmetric, and we call it symmetric because, well, we are guaranteeing that I mean, if torsion is 0, we are guaranteeing that sorry, the Christoffel symbols are 0, right? Because
symmetric.
Yeah, sorry, are symmetric, because when we look at this equation, this term should be 0, and since I mean this term including the k, the vector field k, right? I mean the sum over k, all that vector field should be 0, and since the vector fields, the coordinate vector fields are linearly independent, then these things are also 0, and when paired up correctly, one concludes the equality one desires. Okay. Now,
Now, is there like some kind of geometric intuition one could give for for in the case of torsion free? I mean, or what's the geometric meaning of torsion?
The geometric meaning of being torsion free is that the problem is, I wanted to explain that, but I still don't understand it completely. But the geometric meaning of torsion free is that locally, when you parallel transport, if you take a point, and you look at two tangent vectors, and you parallel transport them, like you parallel transport one, and then there you parallel transport another vector field, another tangent vector. I'm sorry. I'll try to do a drawing. Sorry. Wait. So yeah, we have a point here. No, sorry, I'm not used to doing this. This, and we have something like this. Yeah, so we can think of this as being a curve, right? Of one of the vectors as being a curve and the other one as being a vector. So let's call this P and this W. So we can parallel transport W along P. Okay. And then we will obtain something like this, right? This is the parallel transport of W along P. We have original thing here. And then we can parallel transport, and that's where the problems start. No, yeah, there's no problem. We can now parallel transport B along W. And in Rn, we would obtain a quadrilateral, is the right word? Yeah. I mean, things would look like this, right? This would be the parallel transport of W along B. This is B, this is W. And this would be the parallel transport of W of V along W. And in Rn, this point and this point are the same, right? So that the quadrilateral actually closes. And what torsion-free says is that locally or infinitesimally, but I think it's the right way, this also happens when the connection is torsion-free. But I do not know why. I have been trying to understand the arguments, but they are quite heuristic. So yeah, but that's what it means. It actually has an interpretation. And actually I mean, I haven't talked about them yet, but the Bianchi identities have a similar interpretation, but instead of looking at something that is two-dimensional, you look at a cube. And in that case, it does not close, but it forms a triangle. Yeah, that's more or less the idea.
Yeah. Now, in your picture, I mean, you say you first you parallel transport W along V, but for that, I mean, I guess that what that really means is that you parallel transport W along along an integral curve of V.
Yeah, that's exactly what I mean. That when you begin thinking about it with carefully, you have to ask yourself, what does parallel transport along V means? And yeah, it means that this is really small. I mean, the vector fields are small, the vectors are small, so that parallel transporting along a curved tangent to V is the same as parallel transporting along V. But of course, that actually isn't true, because I mean, a vector is not even contained in a manifold, right? But that's the idea.
Right, but like even in that kind of very small neighborhood, let's say that it's inside a chart, and that the vectors are so small that yeah, that the vectors are very small. I mean, so inside that chart, do you just kind of take the straight line determined by V? I mean, that chart gives you a homeomorphism with Rn, and in Rn, then V somehow does determine like just a straight line.
Yeah.
Parameterized in such a way that the velocity vector is V itself.
Yeah.
So you simply take that curve.
Yeah, I mean, it doesn't matter, right? Because locally, a fixing a vector fixes a curve, right? Every curve that is tangent to a vector is locally the same.
Sure. Yeah, no, but I mean, and then you take any of those curves, and then you do the parallel transport with respect to any of those curves, then.
Yeah, but because they are the same curve, right? I mean, in that very small neighborhood, they are the same curve. As I said,
no,
this
no,
is
no,
not...
no, wait. wait, in the neighborhood, they are not the same curve. They just have the same tangent vector at that point, right? They don't coincide in a neighborhood, right?
No, they should coincide in a neighborhood, right?
No. I mean,
In a small, I
not
mean, not all of them. I mean, yeah, if you, I mean, if you take two curves with the same tangent vector, there is a neighborhood where they coincide. But
no, that's not true. That's not true, because then every curve would be a straight line. I mean,
oh yeah, I see your
there
point.
is.
Yeah, you are right. Yeah, you are right. Yeah, I'm sorry, I hadn't thought about that.
But okay, I mean, just keep going. We can talk about this later when you are done with the presentation.
Yeah.
Carlos, aren't you referring to the fact that the parallel transport is determined locally by 1 point?
But
I mean, we don't really. That's what you were saying yesterday, right? I mean, something like to look at the connection at a given point in order to determine it locally, or am I completely wrong?
No, but wait, what's the statement? What's the precise statement?
Yeah, that's what I do not recall, but I somewhat recall that you were talking about yesterday that indeed we only needed to.
Oh, okay, yeah. I see. I think I see what you're saying. Yeah, that the parallel locally the parallel transport should be determined by the direction in which one is parallel transporting, and not necessarily. Yeah, but I mean, you take a curve, you take a point. I mean, you take 2 points, right? I think that's what you're saying. You take 2 points that are very close together, and then you take two curves. Of course, this doesn't seem. And you take two curves that have the same tangent vector at this point, and then you parallel transport along those curves, and in a very small neighborhood, those two parallel transport should be the same. That's what you said, right? Or what you wanted
Yeah,
to
I
say.
guess.
Yeah.
Right, but then that may be just it. That may be just it, that you take two curves with the same endpoints and the same initial velocity vector. Right, and then you transport. Yeah. Okay. And then you do the drawing that you have above the first row.
And yeah, I think that in some cases should make sense, because we are essentially to parallel transport, we are essentially evaluating a connection, right? And the connection, I mean, it depends on two things, but the direction part depends only on the value at the point, right? The part that depends on a neighborhood is the other one. So yeah, I think this should make sense.
Yeah, although I mean, this would be a way of making sense of, transporting W parallelly along V, and then it would also make sense of parallel transporting V along W. But I think I would still have problems with comparing both parallel transports.
Yeah, that's what I said, that I do not understand why torsion measures to how extent this point and this point coincide.
Yeah, I mean, okay, we can speak about this when you are done with your presentations.
Yeah, I'll okay, then yeah. Oh, sorry. And then we can after if we fix a Riemannian manifold, then we can find a unique affine connection on that Riemannian manifold that is symmetric and that is compatible with the Riemannian metric. And that connection is determined by this formula known as the Kosul formula. That's the Kosul formula. And the connection determined by that formula is called the Levi-Civita connection, right? Okay, and now, so what I mean, the strategy for proving this is to show that if we suppose that we have a connection that is symmetric and compatible with the Riemannian metric, then it must satisfy this formula. And since since the vector field zeta is arbitrary and the Riemannian metric is pointwise a non-degenerate bilinear form, then this means that the connection would be uniquely determined. Okay. Now, because of the compatibility with the metric, using the third proposition or the third version, we have this, right? So yeah, might be interesting to notice that the direction that we prove this is the one that we need, right? So yeah, we sorry. I don't know what happened. Yeah, we use these identities and we add them and use the fact that the torsion is 0. The torsion of the connection is 0. Okay, so we add these two and we subtract the third one. Yeah, we obtain this. And then we have to add a 0 somewhere to pass from here to here. And that's the reason for which we obtain the 2 here. And we use the fact that the connection is torsion-free to obtain the Lie brackets that appear here. And that's the Kosul formula. Now, what else must we do? Okay, and this gives us that if such a connection exists.
Wait, just 1 second.
Yeah.
What do you do with the minus sign in that Z GXY?
Okay. Sorry, where? Here?
I mean, on the very first row of those identities. I mean, this X G Y Z and then plus Y G X Z minus Z G X Y. That's minus sign. I mean, if comparing that with your previous slide, what I guess is that is right. Look, there xg yz plus ygxz plus zgxy, they all have the same sign. So I mean, there's something off, right?
Yeah, I probably made a mistake. That's what's up.
So do you think that in this slide, no, in the previous slide, it should be a minus sign there?
Yeah, I'm quite sure about that.
Yeah, okay.
Yeah, because actually, yeah, I don't know why I didn't notice it yesterday, but yes, it should be that, because if not, the formula would be terribly easy to remember, and it is not exactly because there is a weird minus sign somewhere, right? Because if that wasn't the case, then you would simply have to permute everything, right? Simply let x at g evaluated at y zeta, then y evaluated at x zeta, and then zeta evaluated at xy, and you would do the same with LD brackets. But yeah, I'm quite sure that there's a mistake there.
Yeah, okay.
Yeah, because
but just sorry, just before one last thing, maybe shouldn't the minus sign be in the ygxz? Because you see, I mean, like for instance, consider first you have xyz, then you have yxz, which kind of has, you perform one how do you call it? Not permutation. One transposition.
Yeah, like this.
And then you're right, and then you go to zxy, which is again kind of cyclic with respect to the first one.
Yeah.
So couldn't it be that the minus sign really is in the second term?
I mean, it could be, but I can check the formula. I think that's a better.
Yeah. Okay,
Yeah,
but anyway, I don't want to keep it.
Yeah, but I mean, we can check this. This second, I mean, I'm sure this is right. So this one should be negative. X. And this one should be negative. It was the other way around. Sorry. No, I think the minus sign is correct.
Okay.
Now we now want to prove that there is actually such a connection, and that is easy, relatively easy. We simply notice that the right hand side of the Kosul formula is infinite linear in zeta when we fix x and y, and that means that this expression induces a one form, right? I mean, a function going from a linear function that goes from smooth vector fields to the real numbers. And we know that the metric gives us a correspondence between vector fields and one forms. So we simply define the connection evaluated at xy as the unique vector field that satisfies this equality. That's precisely the correspondence between vector fields and one forms, by the way.
Yeah. So just sorry again in that one. So when you say that it's C infinity linear in Z, I mean, are you really saying that somehow we really consider a function from the tangent bundle of M to the real numbers, kind of, you know, like a, I mean, you say C infinity linear in Z, but the Z is kind of a, you know, Z denotes some vector field that you can change, right? So I guess that kind of you work tangent vector per tangent vector, or like, you know, like that you really take the tangent bundle as the domain of that expression.
You are taking the space of smooth vector fields as a domain.
Okay, sorry. Yeah. Sorry. Yeah, you are right. I mean, you're right. You said C infinity linear, not C infinity. Okay. Yeah.
It's not a smooth function. It is a function that takes C infinite functions. When you multiply the vector field by a smooth function, then it is the same to evaluate a function at the product than doing the product with the evaluation of the vector field.
Yeah. Sorry about that.
Yeah. So as I said, the one form induces a vector field. I mean, when you fix xy, then you have a unique vector field that we denote like this, such that evaluating the one form of zeta is the same as evaluating the metric at the vector field and zeta. And then, one then checks that this defining the connection in this way actually gives us a symmetric, I mean, a bilinear function, an R bilinear function that is symmetric and is compatible with the Riemannian metric. And R bilinearity is simple because of this, right? One sees that, I mean, to see that the sum part, one simply takes the connections, like the sum of the connections, and sees that this equation holds, and it's the same for the product. Did I explain myself? So yeah.
I think it's fine.
The other parts, for the other properties, the only thing you do is you begin with the difference of the things you want to prove that are the same, and you begin and you expand using the Kosul formula, and you arrive at what you want. Okay, and then you have a connection that satisfies, that is symmetric and compatible with the metric. And we are missing something else. Okay, yeah. Now,
right.
The last thing regarding connections that I would like to say is how can one calculate the Levi-Civita connection, right? So we know that that the Levi-Civita connection is I mean, a connection in general is determined by the Christoffel symbols. Locally, it is determined by the Christoffel symbol. So if we give a formula for the Christoffel symbols in terms of something that we know, then the connection is determined. Now, by Kosul's formula, we know that in local coordinates, this holds. And how do we know that? Essentially, we evaluate these, where here we use we evaluate the the coordinate vector fields in this expression, right? Here we take the I coordinate vector field, here the J coordinate vector field, and here the K coordinate vector field. Sorry. These three terms cancel because the Lie bracket of coordinate vector fields is always 0. And then we are only left with these three other terms that are exactly this, right? The first one, I mean, the first term is evaluating the metric at the J and K vector fields, and then differentiating that in the direction of the I vector field, and similarly with the other two terms. So we have this. And now, since point by point, the form, the metric is a bilinear, a non-degenerate bilinear form, then the matrix of its coefficients is invertible. And if this is the matrix of the coefficients, then we denote the inverse matrix by this. And then we simply multiply this equality by the Km coefficient, and we sum over K, right? So we have this. Here I changed the order of summation, and I took and after changing, then we can take the common term gamma ij, IL, I'm sorry. And we are left.
Just sorry, just one second, sorry.
Yeah.
I mean, somehow what you are saying is, okay, certain matrix is invertible. I mean, the matrix of the matrix of the Riemannian metric, right, is invertible. Yeah, right. But I have some problems. I mean, because I'm trying to I guess that what you're trying to say is that you arrange whatever you get on the right hand side of equation 3 into a square matrix. That's what I guess you are trying to say, or equivalent, let's say. But my problem is that on the right hand side of 3, I see 3 indices.
Yeah, but no, I didn't mean that.
No?
No. I mean, you do not understand where this matrix came from, or what is the problem?
No, I mean GKM, that matrix that's the matrix of the metric, right? Of the Riemannian metric. Yeah, and actually that entry, like its entry, that matrix, its entries really vary from point to point, right?
Yep.
Yeah. Okay. Now I do agree that point to point it admits an inverse. That I agree, right? And what I guess is that we are going to use the inverse kind of to solve for gamma Lij in equation 3.
Yeah, that's exactly what I do.
Right. But I want to see it, as multiplying the right hand side of 3, as organizing the right hand side of 3 into some sort of matrix and multiplying that with the matrix G upper Km. But I don't see how to organize the right hand side of 3 into a square matrix, since it has 3 indices, I, J, and K.
Well, one would sum over K, no, over L, right? The thing is that I don't know, why do you want to do that?
I mean, it's just kind of kind of, for me, it's kind of a bit shorter, or a bit kind of more straightforward to see. But okay. But anyway, I mean, just maybe just explain as you wanted, and then I will try to see.
Yeah, but, the thing is that at least how I see it is, I only think about matrix in the left part of the inequality, of the equality, right? And the right hand side, I really do not interpret it as doing anything on a matrix. I simply say, okay, I'll do what I did here in the other side. But
yeah, or maybe let me put it another way. In the left hand side of 3, you have again 3 indices, I, J, and K. Right? L, you don't really have it because you are summing over L. Right? So after you perform that sum, you have 3 indices left, I, J, and K. Okay. Now next you say multiply the previous equality by G Km, right? But who is M?
M is the value is the value or the index for which I will find the Christoffel symbol. So I and J are fixed.
I see. Okay. All right.
Yeah, I think that I can say a little bit more there. I and J are fixed. So I want to fix one of the L's that are I mean, they are varying from 1 to n. So what I'm trying to do is to kill every every index but one of them, right? To just stay with one, that in this case will be M.
Yeah, okay. Yeah, now I understand. Yeah, thanks.
Yeah, okay. So one arrives this just by changing the order of summation and taking the common term. And then since the matrices are inverses of one another, the sum should be the delta LM. And this should be 0 in every case except when L and M are equal. So we are left with gamma IJM, right? And then we simply do what we did in this side to the other side, and that is multiplying by JKM and then summing over K. And then we have what we wanted, that is this equality here, as we are expressing every Christoffel symbol in terms of the metric that should be something that we already know. But well, yeah, perhaps we should notice that even knowing this, it is very difficult to calculate the metric, right? The connection, the coefficients of the connection. I mean, computationally, it is complicated because you have to do a lot of calculations, and it is even more complicated because you have to calculate the inverse of this matrix, and that is usually really, I'm thinking that in most cases it is impossible. And in one case where it is possible, it is when the metric is conformal. The metric is conformal to the usual Euclidean metric. That's the reason for which one can calculate most invariants of the hyperbolic space and of the sphere, because those manifolds are locally conformal to Euclidean space. Yeah, I mean, it has nothing to do with this, but that's also the reason for which working or doing geometric analysis on the sphere is relatively easy, because the fact that the metrics are conformal give you allow you to express several problems in very simple ways. And yeah, that's everything I have about Riemannian connections. I think it would be okay to stop here and leave the curvature part for tomorrow.
Yeah. So tomorrow, what do you plan to do?
I'll talk about the curvature tensor and about sectional curvature, and I will prove that the sectional curvature of the hyperbolic plane is constant, negative and constant.
Okay. So at some point, are you going to compute the Christoffel symbols of the hyperbolic plane?
The thing is that there are two strategies to do this. One, by doing the things coordinate free and proving how the curvature changes when you between conformal manifolds, locally conformal manifolds, and or calculating the Christoffel symbols. That since we are working only in dimension 2, it isn't that hard to do, right? I mean,
okay.
You can. I mean, you can choose what would you prefer me to do.
No, I mean, I think this second strategy is kind of probably more elegant. It's just that since the Riemannian metric in the hyperbolic plane is kind of so explicit, you know, that the formula is so explicit, that makes me think that it would be nice to see an expression for the gamma mij.
Yeah, that's actually the reasoning I had. So yeah, maybe I'll do that. I think that's perfectly fine. And in one of the books that you recommended me, it's what they do. So yeah, I'll do that.
Okay, and then you think you are going to finish tomorrow?
Yeah, that I should finish tomorrow.
Okay, all right. Okay, okay. Then I'll see you tomorrow then.
Okay, yeah.
All right.